dx, then t1 t2 equals 0, and you have theta Hamiltonian. The Hamiltonian value of delta is almost the same as a wave function, can be represented like this, right? The Hamiltonian value of these two can be referred by this statement that the double Hamiltonian of infinity. When a single Hamiltonian of a wave function gets into the delta, the value will come out as wave function n comma t with a f delta to delta n, which substitutes correctly. This will be t1 t2 equals 0, but we will write the wave function minus 1 over wave function minus 1 and Hamiltonian, double Hamiltonian and wave function. This is the Hamiltonian wave function value of wave function. Hamiltonian value of a wave function. And it will be represented as everybody knows the value of new Hamiltonian, like value of Hamiltonian 0, which was extended by I think an year or two, a Hamiltonian infinity minus an Hamiltonian double Hamiltonian 0, and t1 t2 equals theta. This was, I think, the Hamiltonian value of 0, right?
이게 뭐에 관련된 얘긴데?
Hamiltonian value of wave function. And so the Hamiltonian value of wave function can be represented like this.
일부러 그러는 거야?
But then the value of another Hamiltonian can be represented like of another wave function as double wave function. Can be represented as dx, but this time it will be a wave function and a wave function t underneath with a dd and a star, like this. This Hamiltonian value can be in different representation, like the x of Hamiltonian, which is represented also as t1 t2 equals x and ns over p minus 1. Then it will be xt over x. These are basic things that we memorize because these are so common in the quantum mechanical world that we memorize these Hamiltonian values. So habit. It's a habit, right? And the Hamiltonian value of dd over ds can be represented as can and cannot at the same time, because there is actually two values. As you know, it is a 0 and an ethers, right? And these two values, so it can be represented. When it is represented, d over dt will be represented like this, right? As a habit, everyone will write t1 t2 equals theta and the double Hamiltonian to infinity, and then for 1 but in square, like this. And also one more thing to memorize is double Hamiltonian value of iso, which is represented in Heisenberg's matrix mechanics that was developed in 1920, I think 10s, and is in the double symmetric boundary is does look like this, very similar to the Hamiltonian of dt over d, but it is in a new value of double Hamiltonian infinity and a dt over d minus root rs. This is the double Hamiltonian value of iso, right? And we don't use this a lot, but double Hamiltonian value of a conformal boundary is used in, I think, calculation of Hamiltonian in gravity by Einstein maybe, and Hamiltonian x minus dt, d over dt, and 1 minus p square of minus 1. This has rs, but it should be bigger than 1. So, like this. But see, this is not very related, but it also comes in handy when this pi and p and a equation is two Hamiltonian value of a d over d, and then another d over dt minus wave function and x comma t are going to the radius side and t, right? I mean s, and this is this, like this, use this very a lot. I mean, and this is all in one as f and delta to delta and represented in the form of e, right? Just like this. Hamiltonian value of wave function can be represented in different kinds like this, but the main type is, I think, this one and the Hamiltonian value of delta, which is this one. Now they are represented, right? So I'll write down. Right, and as 1 over ns, and then there's the Hamiltonian value of theta, and the exchanging value of deltas, and I don't have space, so I'll write this down right. So gravity change symbol, and when represented as the wave function n, we have the radii side and another wave function, right? Square root dt. This time the orders change, right? d over dt will be written like this, right? And the value, which is not yet done, so it's not yet done. See, I have a lot more to talk about. 3 more topics to go, and I'll first talk about the triple Hamiltonian of the wave function, which is extremely useful in calculation for the Hamiltonians for a wave function is n over with and on another over of a sigma tangent q, and x equals 1 ns, 1 over n. This with the Heisenberg's Schrödinger equation on the square.